Well, hello, I'm Selena Mikolajczyk. Thank you for inviting me to speak today. I am the Chief Battery Technology Officer at Lyten, which is doing lithium sulfur batteries, so one of those advanced technologies that beyond lithium ion that Robert talked about. I've been in the battery space for about 25 years. Piotr and I first met at Exponent, and that's where I did my first battery jobs back in 1999. We were looking at battery safety at that time with lithium ion, which was still a new technology. It was in laptops, but not yet cell phones. Okay. I did a lot of battery failure analysis at Exponent. About 10 years of that. I became kind of the world expert on why batteries blow and go boom. It was an interesting time. There was, pictures of people's laptops catching fire on,
airports and
conference room desks and airports, and this was a big deal. Sony had the big recall. It was a very hot topic. Okay.
Can you please mute the other participants?
A lot of that, came down to proper manufacturing. Some of it to chemistry and a lot to manufacturing. Just about the time I was seeing the second round of the same failures, because first the Japanese had the failures, then the Koreans had the failures, then the Chinese manufacturers had the failures. So you kind of saw the same thing a few times, right? About that time, I was recruited by Tesla. I ran cell quality and some engineering for materials engineering for batteries at Tesla. From about the time we ramped Model S to about the time we ramped Model 3. So it was 6 years, which was a lot in Tesla. I did many things there, many things. From there, I went and I ran a battery battery division at Uber, where we were developing and designing battery packs for both bicycles and aircraft. We were thinking about aircraft, but I quickly realized that if I was going to have the cell makers talk to us, I had to have a more practical application as well. So we did the little e-bikes. My team's battery packs are still on the ground. You'll see them on the Lime bicycles if you go and see scooters that are made by Lime and they have a square battery pack with a handle on it. That was my team's design. So I actually see one of my battery packs in the wild periodically. Uber exited hardware business. They sold off Lime, or sold off the packs and the bikes to Lime. I went then to Panasonic, to the Gigafactory in Reno, Nevada. I led engineering there and shipped about 2 billion cells before I came back to the Bay Area. Okay, when we talk about high-speed manufacturing, we made, on a good day, somewhere around 4 million cells a day. Okay, that's where battery manufacturing gets really exciting, because the takt times, the time a battery is in a process, are measured in microseconds, and the tolerances are measured in microns, right? So it's very straightforward techniques happening very, very quickly. Okay. From there, I went to QuantumScape. I tried solid state for a bit, and 2.5 years ago, Lyten recruited me to run the lithium sulfur battery division. So I've done quite a few things in batteries. It's been quite an exciting ride. So I'll tell you a little bit about Lyten and lithium sulfur.
And I'm really, really glad Robert gave that talk first, because it's the basis for so much of this. Okay, so let's see if I can get this to advance. Okay. So what's Lyten? A very young company. We were founded in 2015, and we're actually a 3D graphene company, a carbon company. The company was originally founded about 2015. People were talking about decarbonizing fuels and making hydrogen. So the company was originally founded to take methane, break it up in a plasma, and produce hydrogen gas, and do something with that black stuff. Well, Boss and his team had a look at the black stuff and realized they were making very interesting carbon forms that are very difficult to achieve otherwise, and realized that those carbons were worth way more than the hydrogen. So they pivoted and started looking at the carbon forms that they were making, and started looking at applications. And so we apply the carbons we make to a few different things. We do some very interesting coatings for the US government. We do some really interesting sensors that allow us to detect all kinds of low concentration molecules. We do working with composites, lightweighting and increasing strength of composites. Some of that includes some work with green concretes. And then we also apply these carbons to lithium sulfur batteries, okay? Which is very exotic and very weird. Actually, what happened was some of the government sponsors had a look at our technology when they were doing the work in coatings and said, if you really have what you think you have, maybe you should try lithium sulfur batteries because they need a carbon. Okay? And so the company's been doing lithium sulfur batteries since about 2018. Okay, so not so long. We are in Silicon Valley. We have our headquarters in San Jose. We've got a graphene fab. We've got a battery pilot line there. And then we just this fall took over the lease and equipment that from Cuberg, which was making lithium metal batteries in San Leandro. They went bankrupt, and we purchased out that facility. So we've got another 100,000 square feet there of battery capable production space. We're still very small at just over 300 employees. The team for batteries itself, maybe 150 members. This is an older slide. We pull people from all over the valley, different experiences, a lot of them from practical battery companies, a lot from academia as well. And it's a very diverse group. So what's the carbon and the graphene we make? Well, graphene itself is the perfect form of plates of carbon, right? All the carbons are bonded beautifully, 6-membered rings. They're resonantly stabilized. The carbons don't really want to do anything with any other molecule around there because they are, very lovely, very happy in their bonding structure. But if you make it imperfect, so you add wrinkles and bends and you make something that looks here like a little bit of a mess, because these are, carbon layers and they've got bends and twists to them. Well, then it gets more interesting because every bend and twist means you have a 5-membered ring instead of a 6-membered ring into the structure. And that is not a perfectly resonantly stabilized structure.
I'm sorry, could you repeat that sentence, please?
Yeah, sure.
Gotcha.
So sure. So when you make carbon in graphite, right, it's all 6-membered rings and they're resonantly stabilized.
Hexagon, yeah.
I see, yeah.
If you make a 5-membered ring, the structure stops being flat, right? It gives a bend.
Okay.
But the 5-membered ring is not as stable as the 6-membered ring. Okay, the carbon bonding structure is not as nicely satisfied. So that bend, that point where you have the 5-membered ring, that's really more willing to interact with the surrounding materials. So what this means is, if you want to disperse this material in a solvent, whether it's polar or nonpolar, you can functionalize those carbon, those kind of non-uniform, non-perfect spots. And the carbon will actually disperse nicely in the solvent system. So where the 2D graphene is notorious
Does it
that,
occur naturally, or do you force it
well, you'll blend it.
to become 5-member from 6?
So the way we make this graphene, it just forms that way naturally. It's a messier process in some ways. It looks very imperfect, and you're like, wow, I would rather have the flat plates, until you try to put those flat plates into water or solvent and they clump, because they don't really want to interact with any of those things. The imperfect material, which has got all these different imperfections in the crystal structure, it disperses very nicely.
It looks like liquid.
Hmm?
It looks like liquid.
Yeah, this is a
It
little,
behaves like,
yeah. The resolution here is kind of weird, but those are carbon layers, right?
15 nanometer, yeah.
Yeah.
Like whiskey on the rocks.
here is what some are thinking about right now.
Yeah, so we do this using a plasma technology. We start with hydrocarbons of various types, and we can make really a variety of different carbon structures. So we can make the flaky pieces, we can make spheres, we can do redeposition. We basically can manipulate carbon. And that's what we do. And then we take those carbons, use them for different applications. So what my team does is we produce and develop lithium sulfur batteries. And why lithium sulfur? So lithium sulfur, I think the first paper we saw with people trying to make a lithium sulfur cell, 1960s, okay? Like all great electrochemistry. People tried this, and they found it was very difficult, because the reality is, although the chemistry is very, very appealing, and the theoretical energy densities are very high, this chemistry is different from conventional lithium ion. Conventional lithium ion, you see the rocking chair, the intercalation chemistry, the lithium kind of inserts itself into crystal structures. Lithium sulfur is different. Lithium sulfur is a conversion chemistry, which makes it more similar to lead acid batteries. What actually happens is lithium with sulfur forms covalent bonds, okay? And you have real chemical reactions happening. So that gets messy, and it gets a lot of different chemical reactions happening, and it's a challenging chemistry to work with. One of the other reasons is because as the lithium reacts with the sulfur itself dissolves into the electrolyte, and you get what you call polysulfides, and those polysulfides want to move to the anode, and want to passivate the anode. And this is something they call a polysulfide shuttle, which is a practical limitation of lithium sulfur cells. So you have to address that. The other thing is that sulfur itself is an insulator. So if you tried to put a block of sulfur down, you wouldn't get much of a battery, because it doesn't really want to move electrons. So you have to have some kind of matrix that is conductive, right? So what does our graphene do? Our graphene provides the conductive matrix, and it controls the polysulfide shuttle. Okay, it's still difficult. It's not perfect. And why do you do this? Well, you do this because if you want to get to higher energy densities, you run out of options. You make your separator thinner, you make your coatings better, you make everything thinner and more, but you run into a limit with conventional lithium ion cells. Sulfur will take and hold more lithium, so you will get a higher energy density. Okay, and the roadmap, when you look at lithium sulfur, says, okay, great, you can hit 300 watt hours per kilo in a cell with NMC or NCA. That's kind of where you top out. If you make a lithium metal anode to go with that, maybe you get to 400, maybe 450 watt hours per kilo. Lithium sulfur has much more potential, much bigger roadmap. People talk about 1200 watt hours per kilo. I think you better cut it in half for any practical reality. So, a real practical roadmap says you should be able to get to 500, 600 watt hours per kilo. Okay. Volumetric, never as good as conventional lithium ion. This is really a cell that's lighter weight. Okay. So its big benefit is the gravimetric energy density to weight. But there's another benefit. Sulfur is very, very cheap. Okay. As a cathode, this is the cathode. So sulfur is the active material. If you go to the most ports on the west, you will find someplace where there is a mountain of sulfur. It's a big pile of yellow. Okay.
Gdańsk.
Yeah, it'll be nice. There's some in Vancouver. There's sulfur at the Port of Stockton. There's sulfur down in Port of Long Beach. Big mountains. You can see them from space. If you Google these ports and look at the satellite view, you will see the mountains of sulfur. Because sulfur is found everywhere. It's anytime you extract materials, you will be pulling sulfur out. So the oil industry produces lots of excess sulfur. Coal industry, everyone does this. Okay.
Wine too. Wine has sulfur in it.
Yeah, but it's not excess.
It's not excess. Yeah, but sulfur is used typically as an agricultural fertilizer. Okay. It is very cheap. We went out to see the guys in the port of Stockton and said, hey, can we get a bag or, get some sulfur? We want to test with your sulfur. And they said, yeah, we'll just throw one in your trunk. And we were like, how much do you need for it? They said, just take it. Okay. This stuff is so cheap. Okay. People don't know what to do with it. That's compared to nickel. Nickel is difficult to obtain. Right now, if you look at where people produce nickel, they produce it in Indonesia, where they are strip mining entire mountains and destroying the villages underneath with the effluent, and you'll see pictures of this. people talk about getting nickel from the deep ocean and collecting these mineralogic nodules that are on the ocean floor around the Cook Islands. Recent studies have said that places where they did trials of this and collected these things, no ocean life left. Like in that deep ocean around those nodules, there's ocean life. And they did a study, they pulled some mined some, and 10 years later, no life where they mined it. And there's some theories that those things help produce oxygen, those nodules help produce oxygen on the ocean floor. There's exciting papers about this, whatever. But,
Nickel-based line.
well, no, it's that the nodules themselves, it's funny because they think there's an electrochemical couple between the nodules that actually produces low levels of oxygen at that depth.
Wow.
It's super weird. I'm like, wow, that's so cool, right? People are back and forth on this, right? But the reality is nickel's hard to get. When you really ramp up battery factories, everyone is competing for the available nickel sources. Putting a nickel mine in the US or Canada takes about 5 to 10 years to bring it into production. It's a problem. And if you look at what the proposed gigafactories were, how much nickel would be required for an NMC based kind of battery chemistry, which is that's that high energy density chemistry. So the Teslas are on either NMC or NCA materials, which is nickel, and then cobalt or magnesium or aluminum or whatever. They're all nickel based. So there's not enough nickel to supply all the gigafactories in the world. That's why people have gone to LFP, which is an iron phosphate based cathode. Iron's easier to get, it's cheaper. The energy density is pretty poor, right? So if you look at the weight of active material in a 100 kilowatt hour battery pack, which is a good car, like a top end Model S, if you tried to get that same range in LFP, you double the cathode weight, just the active material weight.
More than that.
Yeah. If you go to lithium sulfur, you cut the weight in half. Okay. And the price, same thing. You can
Volume?
Huh?
A volume?
Volume is different. Volume is problematic. So lithium sulfur is really for anywhere that curb weight matters, anywhere that cost matters, right? So I never expect Model S to be running on lithium sulfur. I expect it to be running on, nickel-based materials because they're expensive and it's a premium car. But I expect Hummers, bigger trucks, because those guys have more volume to work with, right? Any of the heavy trucks, the semi-trucks, those are not volume limited, right? So they can do lithium sulfur. And then the regular cars for regular people, the cheaper ones, yeah, lithium sulfur makes them actually cheap enough from most people's viewpoint, right? So that's why sulfur is so interesting. It is still a very difficult chemistry to work with. It is problematic. Many graduate students have spent time doing lithium sulfur, and they are still bitter about it 10 years, 20 years later. Okay, I run into a lot of a lot of battery guys at various companies, and they're like, I did lithium sulfur when I was a graduate student. They never work. Okay? it's
Cheaper to hire. Cheaper to hire now.
Yeah.
You still need lithium.
You still do need lithium, but as Robert pointed out, there's lithium everywhere. And the technology problem, there's a lot of people working on that, a lot of stuff working in direct lithium extraction, where you use electrochemical cells to remove lithium from brines. Probably very promising, and really probably the technology that allows the US to unlock most of its lithium supply.
So for lithium, you're competing with all the metals, right? The stainless steels.
Well, I'm competing for lithium. I'm competing with, all the lithium ion guys, right? Because they're all making it.
So that's battery guys.
Yeah. Oh, yeah.
But a lot of it goes into steels.
It goes into a few different places,
Yeah.
right? Right now, the biggest users of lithium carbonates, the salts, are the battery folks,
Okay.
right? But yeah, it goes in. It's not that big an industry outside of batteries.
What about sodium instead of lithium?
So sodium-ion batteries, a lot of people are trying that right now. It's the hot new topic. The Chinese are particularly trying it, and I think it's because the Chinese do not have big lithium deposits, and they need to hedge their bets because the lithium is coming from overseas, and that's the one critical mineral they don't have.
Mhm.
Okay, they're buying it from mostly Australia. Okay, and they're also buying it from Colorado, Chile, and so forth. But they don't have the natural resources for lithium. The U.S. does, and not only does the U.S. have lithium deposits everywhere, but the U.S. oil industry actually is the mining technique for getting this lithium because a lot of it is in brine form and it's in the subsurface. So you could do your regular well, and you could go and you could pull the lithium, you could pull some of the waters, some of the brines, because your well is stratified, right? You're going to have water zones and you have oil zones and more water zones. Some of those water zones are going to be very lithium rich. Okay, you could pull that out if you could do a direct extraction on the surface, pump it back in, right, as part of your oil industry. The U.S. has a dominant oil industry that knows how to deal with a lot of this. The only piece that's missing there is the direct lithium extraction piece and commercializing that. But if the U.S. put their mind to this, the U.S. could actually hold the key production of one of the critical minerals in batteries. They could hold dominance in lithium. But it would require that industrial partnership with the oil industry. But that is something the U.S. could do. Hoping they get there.
I don't see
Elon will make it
one
happen.
Elon
Elon will make it happen.
There is one more comparison that I'm curious about: safety.
Yeah,
Just a little thing.
it is. Lithium sulfur is actually safer. And I can get into why. It's subtle, but it's, yeah.
I'll just trust you that is the case.
But, why do we want to do this? Well, we want to do this because we have the potential to get the price down, the energy density up, the carbon footprint way down, and it's a locally supplied battery. So this could be made on really any continent in the world because sulfur's everywhere and lithium's everywhere.
Can you expand a little bit about carbon footprint? Why that would be?
Yeah,
And
because
why is it negative? Oh,
because you could create the carbons in a decarbonizing process. So you could actually decarbonize as part of the process, right? And particularly if you used like a recycled natural gas or whatever, or you use biogas or something to create your carbon. So it is possible to get to carbon negative.
so you get carbon credits.
Yes.
Huh.
Yeah. But the
So
reason
this
is
is in the manufacturing, right?
Huh?
In the manufacturing,
Yeah.
manufacturing
Yeah.
process.
exactly. Cool.
Where on time scale are we here?
Oh, we're over there. Others.
Oh, here?
left. Yeah.
Here, okay,
Yeah, we're still figuring out how to do this stuff that we're making.
7:35.
Yeah,
okay. So we're here, not here,
not here yet.
okay.
Yeah, we will be closer. The reason is that NMC is carbon intensive to make. Like the cell making itself, that's a manufacturing roll-to-roll mechanical process. That's going to be kind of constant, but it's about the raw materials. It's about the fact that NMC is a process that reduces pretty soft carbon. And for regular lithium ion, the carbon that they use, the natural graphite that they use, that's extracted from one mountain, largely in China. There's also a deposit in Madagascar. It's a natural product, most of it. You can make synthetic graphite, but it's expensive, so people buy a natural product. They then leach that with a lot of chemicals to remove all the basically silicon and calcium and other things that are in there. And then they do a bunch of carbonization processes that are very big CO2 emitters. Okay? And I've seen these processes where they take a bunch of this graphite and they put this in these large crucibles and they bury them under raw coal, and then they put electricity through those crucibles to carbonize that stuff. Okay, and then the coal is kind of insulating, and then over the top of the coal, you see the like vapors of PAHs and volatiles coming off the coal, and it's sort of burning on the surface, and all of this is under a big hangar in China, right? It's like, wow, okay.
You don't want to go inside, huh?
Well, yeah, I was inside, right? And I'm looking at this and I'm like, this will never happen in the United States. This would never be permitted in a million years, okay? So when people talk about bringing like the raw material supply chain into the US for a conventional lithium ion cell, they don't realize just what that looks like, how dirty it is, and how much CO2 emissions are involved. There's a reason China did this. There's a reason they're dominant, but we probably don't want any part of it, okay? It's like very eye-opening to see this, okay? That's why they have a big carbon footprint.
Remind me, please, what is NMC? What does it stand?
Nickel, metal,
Nickel.
Carbon,
cobalt.
Oh,
and
cobalt.
LFP. Yeah, that's the cathode. Right?
cobalt.
So what does our battery look like? So, as you say, simple structure, anode, cathode, there's a separator in there. What are you going to do? How do you make this? Well, your cathode in conventional lithium ion, this would be either NMC, NCA, no. It would be LFP, that's what a cathode is, okay? For our cells, it is sulfur in a carbon matrix. Okay. For the anode, you do metallic lithium. We started with that. We realized that lithium was deeply understudied. We're actually moving to alloys and composites of lithium, which we find are much more stable and much more useful. So there's a lot of work that can be done in lithium metal anodes. People have not done it because lithium metal is a little terrifying to work with. Very few people have the equipment to even look at it, right? So to even look at how the lithium is evolving in the cell, you need a focused ion beam, a FIB, SEM, right? And otherwise, you're doing very empirical things, right? And then if you want to create these alloys, you have to create them yourself, which means melting lithium in a crucible in a glove box, mixing other things in it, and then rolling and extruding that. Most people find that daunting, but we're actually doing it in our facility, right, to develop this. So there's a lot of room to develop lithium anodes to improve cycle life. So, what our roadmap looks like, these are normalized watt hours per kilo to our pilot line cell. But, it's been a slow, steady walk up the cycle life curve and up the energy density curve. Okay. One thing about lithium sulfur is the cycle life is always the most challenging part of this, right? These are full depth of discharge, practical cells, 25C, we're getting 300, 200, 300 cycles. Most people in the battery world are like, really? You're doing that well? In a practical cell? I'm like, yeah. Most other people find that underwhelming, okay? But the reality is that this is a full depth of discharge cycle, which very few batteries actually see. So most of your cars, any kind of stationary storage, you tend not to drop the battery to zero. You tend to do a partial depth of discharge. And under partial depths of discharge, these cells will go thousands of cycles. So we've been making...
I'm sorry,
Yeah.
maybe I missed something.
Yeah.
So high energy, high power would be probably the best what I could get, right? The other one is balanced, and it looks to me a little bit better. So what I'm missing?
Well, it's about this number here. Like, what's that number? There are some people who really, really want this number for a few cycles.
Okay.
All right. They tend to have somewhat disposable.
So it's a trade-off.
Yeah, it's a trade-off.
Trade-off.
Yeah. A balanced cell is where we spend most of our energy. That's most people's interest, right? That's something where you have enough energy density and enough cycle life, right? And we have ambitious targets.
Yeah.
We're actually on trend for them. It's okay. It's hard as hell, but we are on trend for these things. And the other thing you should look at is that the traditional lithium ion over time improvement has been something like 4% per year of capacity increase. Okay, that is over time what lithium ion has done. Okay, we've been doing somewhat better than that. We're about 12% per year in energy density increase. On a R&D standpoint, it's a lot of work, right? But still, we make actual practical cells. We're actually cycling them and making progress. And we've got cells that they'll make 250 to 300 cycles at a full depth of discharge, and at 20%, we're well now beyond 3,000 cycles. We think that'll go to 5,000 cycles. So, this is a cell that can be used now for certain applications, things like micromobility, some stationary applications, drones, and that sort of thing. We actually have a practical cell that can be used and can be interesting. The other thing about this chemistry is that it is a conversion chemistry. It is driven by these chemical reactions. So what happens is when you raise the temperature, you get more capacity and you get better rate capability and everything else. So where this cell would do about 250 watt hours per kilo at C/3, right there. Okay, if I go real slow on it and maybe raise the temperature a little bit, I get to close to 350 watt hours per kilo. Okay. You can see this here too at different temperatures, right? I'm going from a cell at 25 C, this 250, 240, to about 280, right, in capacity. So that's kind of a nice bonus. You don't see that much.
You want to run it hot.
Yeah, you want to run it hot. The other thing we've been looking at, and I don't have the charts, I'm sorry, are calendar life. So if you set the cell on the bench and just let it sit, it will degrade. Okay, this is, as you say, it's a living thing. And as you know, if you sit your body on a couch, it will degrade. And if you go and exercise every day, you'll also degrade. It's just a question of degrade. Okay, so calendar life with cells. SEI, that SEI layer is a continuing chemical process, and it eats lithium and it eats electrolyte and other things. We're finding with this cell chemistry, actually, we get very good calendar life, which surprises people. Lithium sulfur traditionally has been thought of as very poor. What we found is once you make that passivation layer, the cell is very, very stable. So it sits at the same, at 100% state of charge. At high temperature, low temperature, doesn't matter.
But then it dives down.
This is a capacity
Capacity.
versus voltage.
Yes. So is this,
So what
Okay.
you see with cells, right, you have a discharge curve, and you'll hit some cutoff voltage, and then there's not really much real capacity left, right? So it's a voltage curve. Lithium sulfur is weird. This is the other thing that's weird about it. It has this two plateau. So this is a plateau where you're making kind of high, you're dissolving sulfur here, and then here you're precipitating a salt, an Li2S salt, largely, right? And then you get to a point where really there's not much snooze left, no capacity left, so that's when the voltage drops off, right?
So is that like an aging curve? What you're showing?
no, this is not
just the
time.
voltage and discharge curve. So if you're building a piece of microelectronics or electronics, right? Kind of look at this, and this scares people because they're like, well,
When it's discharged, you just lose voltage.
Yeah.
At the end.
yeah, which is true for every cell.
Time to charge here
Exactly.
and come back.
This has some challenges for electronics development, but it's not too terrible. It's actually because of the way the cell is resistant to overcharge. It's not that hard to actually implement this cell. It's kind of gives you some grace in its charge profile.
So that plot over there on the left, that's the reason why Tesla is warming up batteries before charging.
Yes, it is. Because what happens with a battery, right? It's all diffusion. And you've got an electrolyte, you've got a salt moving through an electrolyte.
Accelerated diffusion.
When you drop the temperature,
Yeah.
it all slows down, right?
Yeah.
And we're actually, this cell is pretty good down to lower temperatures. The first plateau, you get that capacity out, but you start losing that second plateau because that chemistry slows down a lot when you get really cold, right?
But when you leave the car at Tahoe outside, you have a limit.
You do. You have to do something.
Yeah.
And that's going to be true, by the way, any chemistry, because it's all diffusion and chemistry.
Right.
So we all know chemistry slows down at lower temperatures.
Right.
It's,
Cool.
let's see. All right. We talked a little bit about this, about the cycling. The other thing we're doing is we're making all our cells on conventional lithium-ion making equipment. So all of the gigafactories that are announced, all the equipment makers, that is a lot of technology development in its own right that's been happening over the last 30 years. So if you want to scale this technology, you better put it and make it on machines that people are already making for cell making or something equivalent, right? That is what this chemistry does. We actually do this all on conventional lithium ion making equipment. So we have to make our own cathode active material. We have to modify equipment slightly, but not a lot. But we use all standard lithium ion equipment. So let me see if this will play.
Selena request from Zoom. If you could flip back to slide number 12, please.
Jelly rolls for cylindrical cells, right? Pouches typically used for anything that people want really slender. They have the best energy density. This contains a pouch cell. This contains a pouch cell. The typical pouch cells you see, like for remote controlled aircraft, those are all pouch cells. They're stacked or wound, but usually stacked now.
Mhm.
Cylindrical cells are actually faster to make. They're cars. Yeah, and you can make them at high volume more quickly. They are, the production is sometimes a little trickier, but like I said, it goes faster.
Why do you have to make thousands of little tiny cylinders instead of big cylinders?
Well, there's a few reasons for that. One is the safety issue.
Okay.
So a cell contains a lot of energy, right? If a small cylinder releases that energy quickly, you can dissipate it, you can manage it. You get a big cell,
Okay, got it.
way harder. Okay?
Yes.
So safety is one of them. The other thing is, if you make a little cell and it's got a defect in it,
Yeah.
you reject it. If you make a big cell and it has a little defect in it, you have to reject it.
Yeah,
Okay?
yeah.
The cost differential, the
Huge.
scrap cost, production reality, is that for the cell manufacturer, it's a lot easier to make a small cell and reject, even if
Yeah.
your scrap rate's low, it's painful.
Yeah.
If you have to reject all that electrode, it's really painful.
Got it.
Same paradigm you were talking
I know.
about in the last,
Right,
in the
exactly.
last presentation.
Yeah.
How do you work with lithium? Thank you.
So lithium is not as terrifying as everyone thinks. In the metallic form, right? You can handle it in a dry room. Okay, so you have a super dry room, and you need dry rooms for most of these chemistries anyway. If you look at the high performing cells like the NMCs or NCAs that are in Teslas, those cells are made in dry conditions in dry rooms. And if you go in those factories, you walk out of them feeling like a raisin because you've been at minus 35 degrees C dew point in the dry room. Okay, it's that dry, and that's to actually protect the nickel industry. LFP is a little different, doesn't require as much drying, but it still requires some because all the electrolytes, the lithium, react with moisture. So anywhere that you've got electrolyte, you have to dry anyway. So putting lithium metal into that dry room is actually okay, and you can manage it. So where are we? Now, we have about 2 megawatt hour line in San Jose, where we produce pouches and cylinders. And then we just bought that Kubrick facility, so we're putting about 100 megawatt hours in there over the next year and a half. Okay. And then our long-term plan is we've got putting a gigafactory in Reno, somewhere 6 to 10 gigawatt hours. It's kind of modest for gigafactory scales, but this is actually a good scale to supply micromobility, stationary, heavy truck business. It's not automotive scale. Automotive scale would really mean you're going to somewhere on the order of 50 gigawatt hours for a really, good automotive scale cell line. So we're kind of stepping step by step through this, but that's looking mid 2027, maybe 2028, depends how we go. But that's kind of how we're planning to scale this up.
Okay.
No issue with demand.
So, I'm not worried about demand. I'm kind of like, there's a lot of people calling us who want to try our cells. Is the technology where everyone wants it? I mean, the car guys, no, it's not ready for the car guys. Okay. It is ready for the micromobility guys. And then we think the high temperature performance, or the performance at temperature, is probably going to be much better than the NMC and LFP batteries. So we think this is a cell for the global south, right? So we think this is a cell for stationary for the Caribbean islands, anywhere that's kind of warm, right? Right now, under those conditions, either people have to heavily refrigerate their stationary packs or they degrade within a year or two, right? Which is not what you typically hear about. Usually you hear about these long cycle lives for LFP. All that testing is done at 25 degrees C. Okay. The question of survivability and actual usefulness at high temperatures where a lot of these packs are needed is not really covered very well. So little micromobility packs for e-bikes and other stuff, they don't come with cooling systems. And they are all over the global south. And their lifetime is pretty short. Okay, we think these cells are going to be really competitive and really interesting compared to that.
So it's a contradiction. You said, at high temperature, they work better,
Yep,
but then they degrade faster,
conventional ones do.
conventional ones.
Yeah.
Okay.
Yeah, we think we think we've got a less degradation mechanism
Okay.
for the higher temperatures.
Is that why Honeywell is investing in your company so heavily? Honeywell?
Honeywell? No, Honeywell's interested in our sensors.
Oh, okay.
They're interested. I mean, they're interested in batteries, but mostly it's sensors.
Okay.
Yeah.
FedEx is joined investing.
The FedEx guys are interested in our cells for their last mile delivery trucks. Right, so if we took our cell and put in a last mile delivery truck, we've done the calculation. They can carry about 200 more kilos of packages. Right? So that to them is a big deal because they're using regular drivers, non-CDL licensed drivers. So they have a weight limit on their delivery vans and it limits how many packages they can put in there for delivery. Right? So if we go to a lithium sulfur versus conventional battery pack, they can put more packages in there that matters to them.
Fascinating little implications. Incredible.
Yeah, it's like you're like, why would you care? FedEx cares, right?
Ready for a Tesla question?
Sure.
So I had a heavy foot on my gas pedal.
Yeah.
And I step on it. And have you ever seen a three-phase motor? When you are doing this, you are switching two phases, and it wants to go full blast in the opposite direction. That's what I felt. I stepped on it. I got a full blast backwards, like I hit the wall. Okay. At that moment, the car loses all the power. Then I notice that I have about 5% of power. I pull over, call Tesla support. They are telling me, okay, let's try reboot. I did the reboot, and the car goes like nothing happens. They take the car into service, and when it comes back from service, it comes back with a new battery. That's a puzzle for you.
That is a puzzle.
How can I do the same? I would like new battery.
Try to step on it. If you're within warranty. I could not figure out why they changed the battery and why a reboot revived my car from literally I had like 5 kilowatts to just pull over and stop. And when I stopped, it just stopped for good.
Okay.
And after reboot, it totally woke up.
We have to repeat that
not
under
a
supervision.
It's the sensor which is reading the battery.
Usually when you ask Selena this kind of question, it's about $250,000 to $2,000 per hour.
Like a true consultant.
Okay.
I have no idea. I'm
Okay.
not the electric motor guy.
All right.
I would say I know that to get at the electric motor, you have to drop the pack anyway.
Yes.
So maybe they dropped it, checked it, and said this is not so great.
I see. Okay.
Dealt with something else.
Maybe battery unrelated. Okay.
Maybe I don't
I'll
know.
buy that. The second question. So my second accident was I drove a little bit too far on my battery. But I still had 5% left, no, less than 5% left probably. I come to a supercharger and I cannot open the little flap covering the outlet.
Uh-huh.
And I lost the 12-volt battery.
Oh, yes.
In the process, why did I lose the 12-volt battery by discharging the big battery?
Okay.
Have you
Because you did that acceleration before.
What do you using a lithium sulfur battery?
Okay.
I'm using whatever Tesla put in it, and they hide it well.
Okay, so I'm gonna make a real guess here.
Okay.
Real guess. So the fuel gauging, right, that tells you how much capacity you have left, it's a model, okay?
Yes.
And there's gonna be some margin of error, okay? It tries to model what your battery has, but it gets a little foggy down at that bottom of capacity. It's just a little difficult to actually predict
Okay.
where you are and what's going on, because depending on how fast you did the discharges,
Mhm.
it just doesn't quite know exactly. So it's always a little bit of, you know,
Okay.
it's a little unclear, right? Sometimes you have more energy, sometimes you have a little less.
Yeah.
Okay. I know that the 12-volt battery is designed to make sure that if the main battery fails, there's not enough power, it will continue to power your brakes and your, windshield wipers and your
Yes.
lights. And so that's what it's designed to do, right?
Uh-huh.
So if you lose the connection with the main battery, you don't crash, right?
Right.
You get some.
Yes.
So unclear whether that was engaged or not, whether you lost your main pack. The 12-volt battery, though, also, it's a battery, right? And it was never really designed to cycle.
Okay.
12-volt batteries, lead acid batteries, they're not good for cycling. They're good for slow, quick discharges, right? You've got that cold cranking, in a conventional
Yes.
car. It's the same sort of battery. How old's your Tesla?
2013.
That's mine too. Yeah,
That's yours,
early.
yes.
That's his.
That's
too.
why I'm asking you.
Yes. Yeah, that's the early stuff. That car doesn't sleep as well as the other cars. So when you turn it off, it tends to draw a little more from the 12-volt.
Yes.
Mine discharges more when it sleeps
Yes.
than when I drive.
Yes, exactly, right? So it's got these vampire loads on it. The car was actually originally designed to do a very deep sleep. And the battery was supposed to be fine for it. And then Elon looked at this and he said, customers don't want to wait that long for it to wake up, right? And the engineers had designed this thing to sleep, right? To really turn everything off. But, computers take a little while to reboot. And Elon didn't like the reboot time, right? And the wake up time. This was like a whole thing back in 2012, 2013. So they got rid of the deep sleep and a lot of things stayed on, right?
Yeah.
Elon made sure that a lot of stuff stays on. So when you get in the car, you can go. This put a lot more loads on the battery, on the 12 volts, and it wasn't designed for it, right? There's some differences in the hardware in later cars that mitigated these problems, but the early cars, ours tend to eat our 12-volt batteries periodically.
Oh.
Okay. And just because the battery gets weaker because it's cycling, right? And so there's we put in firmware that would detect if your 12-volt battery is going bad and let you know that the 12-volt battery needs replacement. It's not perfect, but it's there.
Yeah.
And the
So
other
that worked once, yes.
Yeah, exactly, right? Yeah, and then the other thing that is another quirk of electric vehicles, right? That you think everything will be fine, right? Oh, yeah, everything's good. So when you have your regular car, right, and you're cranking it cold, right, and you crank the battery, you put this big current load to it, and eventually your battery dies, right?
Yeah.
You call the AAA guys or something, or they measure it, the impedance is too high and everything else. Right, well, that's because that's basically a test every time you turn on the crank, right? That battery is putting out a lot of current, and so, you can see that it's bad. In a Tesla, even that vampire load, it's very gentle,
Yes.
right? So
So-
you never get that cold crank.
So
test.
one killer question about this whole incident. When it went into service, they gave me an offer I couldn't refuse.
Uh-huh.
Change the motor. $9K.
Marek, may I suggest that
Yes.
you hire your consultant separately?
We'll do that, sir.
People will go, they go there,
Okay.
it's 8 o'clock.
Yes. Thank you. Thank you.
Pure jealous. First you got the battery for free, then you got the motor for free. You're making people
Yeah, but I will, just to end the story, I was highly motivated to organize this meeting.
I don't know why you were dragged.
Well, and on the screen, you see another reason, another motivation. My house is running now on a Tesla battery.
No, but the question here, which I would have about the batteries which you are saying, which are, more volumetric,
Yeah,
would they be good for power walls, something like this application, or it's too
Probably.
expensive, or?
no, I mean, this is, like I said, stationary, like, especially behind the meter stationary, we think is actually gonna be a very big business for these batteries, because they're cheap, right?
Mhm.
Yeah.
Fundamentally, the cost is down, the volume doesn't matter so much,
Right,
right?
Yeah.
It's a good installation
Yeah.
for a garage.
yes.
Yeah, and then, well, I mean, it doesn't matter that much, and then they're lighter weight, so they're easier to install, and there's kind of, a bunch of benefits that we think that could be a very,
Okay.
nice application for this.
So are you guys public?
Nope.
No.
You're going to invest in this mega fab? Giga fab. Let's do it.
I'm gonna watch.
Let us know when you take money.
When are you going, when is your IPO?
We just concluded Series B.
I know.
Yeah, we're got a C series ahead of us, and everyone is asking the boss, when do we IPO, but I don't know, that's, I want revenues first, like, good revenues, yeah.
Thanks.
FedEx was a major player in that cycle.
Okay, thank you so much, Selena. Robert, thank you so much. That's it.